good afternoon, good evening, and good morning in which time zone you are. Today our president, Professor Rodrigo Martin, is not here, and he has got some urgent work when he's traveling. So before I proceed, I think I will request Sara to play. He has recorded a message for us. So Sara, please play the message, and then I will continue.
Dear Ho, as President of the European Academy of Science, I have the great pleasure to introduce to you on this set of webinars that we are organizing, Professor Grätzel. Professor Grätzel is a pioneer in molecular photovoltaics, whose contributions have revolutionized the solar energy conversion. His work is the pioneer in developing the new era and the new strategy for the new impact solar cells perovskite based. The title of his talk, Molecular Photovoltaics and the Stunning Rise of Perovskite Solar Cells, is really a milestone for all of us, and we have the honor to listen in the next 35 or 45 minutes Professor Graetzel. Thank you very much, Professor.
Thank you.
Thank you, Sara. Can you put my screen? So again, good afternoon, good evening, and good morning in which time zone you are. Dear colleagues, guests, member of the Presidium, researcher, ladies and gentlemen. I am deeply delighted to welcome you to attend the second seminar series of European Academy of Science, and is our opportunity to engage with the global leader for science and society. This conversation is being recorded and also live on YouTube and will be available on our YouTube channel. My name is Shahzada and I'm a professor of material science. Today, for the next 1 hour, I am joined by Professor Michael Graetzel. I have a great pleasure of introducing him today and knew him for nearly 2 decades. Allow me to quote Nigel Hamilton. Nigel Hamilton, the biographer of John F. Kennedy and Field Marshal Montgomery. Montgomery was a veteran of World War II. He's a commander-in-chief of World War II. So allow him to quote. So Nigel Hamilton quote, biography is simply the orphan of academia. If a leader does all that the historical forces make indispensable, then the person is not as important as the moment. In this context, if you look at the career trajectory of Professor Michael Graetzel, it endorsed Nigel Hamilton. Graetzel studied chemistry and earned his doctorate in the physical chemistry from TU Berlin in 1971 and habilitated from Free University of Berlin in 1976. Since 1977, he has been a professor at the EPFL, École Polytechnique Fédérale Lausanne, where he directs the laboratory of photonics and interfaces. Graetzel discovered molecular photovoltaics, being the first to conceive and realize mesoscopic photosystem based on molecular light harvester that convert light to electricity. He is credited with moving the photovoltaic field beyond the principle of light absorption by a diode to the molecular level. His revolutionary design approach made a new paradigm in the field of photovoltaics. Today, the perovskite solar cells that reaches the solar to electric conversion efficiency of 27% emerged from his lab. His research also led to the advancement on lithium-ion batteries and photoelectrochemical cells for solar-driven water splitting to store renewable energy and CO2 reduction. Grätzel work has been summarized in nearly 2,000 scientific publications, which have received nearly 500,000 citations with an H-index of 300. A recent ranking issued by Stanford University places Grätzel in the first position on a list of 100,000 top scientists across all fields. He received honorary doctorate from 14 leading universities across the globe, member of 12 foreign and national academies, and delivered over 50 indoor lectures. And if I want to mention all his prizes and merit, I may need another 30 minutes to keep going on and on and on. So just please allow me to list only of the key recent prizes. Among them is BBVA Frontier of Knowledge Award in Basic Science, the Global Energy Prize, the Centenary Prize from Royal Society of Chemistry, the Prize of the Swiss Chemical Society, King Faisal International Science Award, Leonardo da Vinci Medal of our Academy of European Academy of Science, Marcel Banner's Prize, Albert Einstein World Academy of Award of Science, Swiss Electric Award, Gutenberg Research Award, Galileo Galilei Award, Millennium Technology Grand Prize, Balzan Prize, and the Friday Medal from the Royal Society of Chemistry. He has over 5 decades of active engagement in academia and research and development and inspired a generation of scientists among me. Ladies and gentlemen, it is fair to say that he is among the most decorated scientists in Europe we have today. I cannot imagine a better expert available today on electron transfer reaction than Professor Graetzel. Today, Grätzel will enlighten us and share his expert knowledge with his talk, Molecular Photovoltaics and the Stunning Rise of Perovskite Solar Cells. Grätzel, dear Michael, thank you for accepting our invitation and all our members for their engagement. And with this, I want to pass the floor to you. I also have a time history of dye-sensitized solar cell, how from the first Becquerel sensitization to your discovery, the landmark in 1991 paper, we came to solid-state DSC, and now the Chinese company Utmolite is making a large panel of perovskite solar cells, which also stem from your lab. With this, I think I pass the floor to you.
Thank you. Thank you, Shahzada. It's very kind words, and also for the invitation, which is a great honor. So I will share now my screen. Well, it's a pleasure and honor to give this talk at the European Academy of Science. And yeah, the lecture will be on molecular photovoltaics. And inspiration came from the famous most famous molecular photovoltaic system, which is the green leaf. And so out of this research emerged also a new technology, which is the perovskite solar cells. And at this stage, we have 400 companies in China making those cells. So I just wanted to, this afternoon, to describe to you a little bit our journey, how we got there and where we stand today. And so inspiration, everybody who works in this field wants to develop clean and renewable energy resources. And so, so it's clear that oil will go down and hydrogen will emerge as a major energy carrier. This is actually, this data comes from a shell analysis. It's called Skies and Now. You can find it on the internet. And so the issue which we are, the challenge which we are facing is that within the next, say, 20 years, we should have 75 terawatts peak power installed. However, at the present rate, so in 20 years, we would have to reach that goal to meet the targets of the Paris Climate Agreement. However, I mean, at present, we are installing at a rate of 300 a year instead of 3 terawatts a year. We have 300 gigawatt a year. So it would take 250 years to reach this if we continue. So that's a challenge. We have to speed up. And so new technologies may have to kick in. And so one of the emerging technologies is the dye-sensitized cells and perovskites. And as you can see, the silicon use a lot of very highly pure material. For 1 megawatt installed, you need 7 tons of silicon. And 1 megawatt is not all that much. There's a peak power installed. And so, but you see perovskites and dye-sensitized, they're much lower, almost a factor of 1,000 lower. So here's the attraction from the point of view, just materials and the high purity of silicon, 99.999, there's 9 nines in that number. So this costs energy, and so energy payback time is quite long still, several years of silicon cells. While for the perovskites, for example, it's only a month. And we also note the high carbon footprint of silicon. Why is that? Well, to make silicon panels, it takes a lot of energy, and so how is that produced? Well, mainly from burning coal. That's highly polluting, and so we have, for each kilowatt hour, we have 50 grams CO2 emitted. And so if we would cover all these 75 terawatts I was showing you by silicon panels, I mean, this kind of CO2 release would be many gigatons. And let me remind me, we want to get to zero CO2 emission from currently 40 gigaton per year emission. And there's also the recycling. So that's something one has to think about, because there's a tsunami of PV panels that is trying to reach us soon. Yeah, so let's now go to the core of my lecture. As I said, the inspiration came from the photosynthesis, and yeah, that led to the two innovations and the dye-sensitized solar cells, and the second revolution, perovskite solar cells, which today have close to 27% power conversion efficiency. And the dye-sensitized cells have meanwhile been commercialized. And they are not competing with silicon. They have their own markets, like these panels that collect vertically the solar radiation. And there's also now a large production capacity in commercial products that use ambient light to power electronic equipment. Yeah, so as I said, it's our inspiration. It's a molecular system. And let me just remind you that the stored power, so this is the power produced by photosynthesis, but in form of stored chemical energy, is 32 terawatts. That compares to the, remember I mentioned the 20 terawatts we are presently consuming. And so photosynthesis is a major source of our renewable energy. And so, yeah, the molecular systems emerged from a study that was actually done by Professor Goodenough and published in Nature in 1975. At that time, he was in Oxford, and we became friends. So he had sensitized the planar titanium electrodes by a ruthenium complex. And as you can see, actually it was the right approach. He used the ruthenium complex with the attaching groups, these carboxylates that would coordinatively bind to surface titanium ions. And this is a self-limiting process. Once you have saturated the surface sites, there's no more dye adsorption. So it's a way, just by a simple dipping, you can make a self-assembled monolayer on the electrode. In his case, he had used a single crystal Ti2 electrode, and what he observed was there was some electric current produced under light. However, as you can see, the current level is very small, 70 nanoamps per square centimeter, which with a reasonably high intensity light source. And so, yeah, that was, it's about 5 orders of magnitude below that what a silicon cell would produce. And so in these days, when we started our research, this method was decried as being highly inefficient and not promising. And so everybody was going for silicon and other technologies. However, we had a different approach. We had been working on colloidal semiconductors, the first actually to investigate those colloidal semiconductors. And we had found that we could sensitize those colloidal particles very efficiently. Injection rates were much faster than recombination rates of carriers. And so we took a patent out in 1988, after we had done some model studies on a high surface area electrodes. And so that patent was the base for the DSC development. You can see that here's our patent, and then these patents came afterwards. These are still our patents, but today we have close to 5,000 patents in the DSC field. And yeah, and as I said, how did we achieve that? How did we have the idea to use the mesoscopic electrodes. Well, as I said, we had done a lot of work on these colloidal semiconductors for years. It was a fundamental studies, curiosity-driven. But we noticed here, you see there's a paper, photosensitized electron injection. That really was a key paper which inspired us. And so finally, the structure which evolved from at the end was, or at the end, in the beginning of the 1991 paper that Shahzada mentioned, was an electrode consisting of an array of nanoparticles of semiconductor oxides, TiO2 in this case. And so, yeah, so we could form those films very easily by screen printing, and the colloids were easy to make. And so you can see on the left, you can see a SDM picture of the colloidal film, and you can see the TiO2 nanoparticles annotates. And this is the 101 facet, this facet you can see here. And that's actually prevalent facets on those particles. It's the lowest energy facet. And so then by dip coating, we would cover this nanocrystalline array with a dye like the standard became this N3 dye named after Dr. Nasruddin, who was a postdoc at that time in our laboratory. And yeah, same anchoring groups that Good Enough had used, but the dye was not the same structure. This was much better in visible light absorption. And so at the end, I mean, when we compare the planar surface that Professor Good Enough, who later won a Nobel Prize for his battery work, we compare that, cut the same surface facet with a single crystal, and this disordered array of nanoparticles. We found that we could increase the photocurrents over 1,000 times. That was the breakthrough discovery. And you can see here the PC, the IPC, that's the external quantum efficiency. So 80 or 90 means out of 90 incoming photons that strike the cell, out of 100, 90 will be making electrons. Okay? Yeah, and so we understood that phenomena by doing a lot of fundamental studies. And at the end, I mean, the physicists first were very skeptical that we couldn't. They agreed that we could inject electrons in these particles, but the collection was a problem for them. So there was no field to separate positive, negative charges, and also the diffusion was very slow in these systems. However, we found that we analyzed by impedance spectroscopy using the transmission line model developed by our colleague, Professor Juan Biscuit, who is now in Valencia, a professor. We could determine those resistances easily. I mean, that was really a very important study that Professor Juan Biscuit initiated. And so these resistances could be measured, and then we could determine the transport and recombination time from these of electrons, and that gives the collection efficiency. So finally, we find it's easy enough to say if we have if the transport is 100 times faster than recombination, then I mean we will collect all the charge carriers. 99% at least. And so, so let me move on to the next slide. And so, and I just want to close the window. There's some noise here. So yeah, at the end, I mean, these studies culminated in the paper we published together with Brian O'Regan in 1991, and that reported on these cells which, as I said, consisted of these nanoparticle arrays covered with a molecular sensitizer. And then it's very simple. I mean, you just need a collector, conducting glass at the front, and and at the back side. And yeah, this is how the cell can be made. And you see one of those devices here. It looks like a colored glass plate, but it's a photovoltaic cell. And in ambient light, it turns this fan. That's one of the features of the dye-sensitized cells. They're very efficient in ambient light, and that has led to companies like Ambient Photonics that make devices that are special, especially highly active in collecting ambient photons. So yeah, this paper has actually over 37,000 citations now. And so it's probably one of the most highly cited works. And here's Pine and I at a meeting. Yeah, now let's just look at the energetics for a minute. So we have that excitation, the light, electron is injected, goes in the external circuit, comes back, and now we have to shuttle it back to the sensitizer. So you need some kind of a redox shuttle. It could be a solid state whole conductor or redox couple. Initially, we used iodide and iodine. And that was not a good choice from the energetic point of view, because you can see that half of the photon energy was lost in a regeneration reaction. So in other words, the oxidized dye gets reduced back to the starting state using iodide. However, the energetics are not very favorable for photovoltaics. And so there is a big voltage loss. So our cells for a long time, they had troubles getting more than 10% efficiency. 10% was kind of certified, or a little bit over 10%. And but today we have this issue was solved. And but on the one hand, we new sensitizers were developed, and these are organic type sensitizers. And you can see that here, for example, we have a donor acceptor type molecule. And so when you excite this dye, the electron flow from the donor to the acceptor, from the top and to the bottom. And the acceptor is linked to the Ti2, which is ultimately receiving the electron. So these are rationally designed molecules that work very well. There are many variants, but here I mentioned the work of pioneering work, I should say, of Anders Schagfeld, but also Professor Marina Freitag. She actually came up with a copper complex that is really an ideal match for the sensitizers we are showing here. And so the energy loss in this regeneration step of the sensitizer is very small, 100 millielectron volts compared to 500 millielectron volts in the iodide case. And so that has driven the efficiencies up and also promoted the commercial application of these systems. And so here's one example of a green dye that's a porphyrin derivative. We have a donor, we have the acceptor, and we have the chromophore in the middle. And so these very beautiful green colored dyes, they obey the same principle which I had shown you just a minute ago. The donor function is up there, and then the acceptor down, and this is the Ti2 lattice. So the electron flow from top to bottom when light hits the dye. And so this has given rise also to optimized structures. And here we have the first dye-sensitized solar cell that achieved 13%, was published in 2014. And that paper also is a very highly cited paper, because you can see in the black dots here that the whole visible range, a single sensitizer, can capture the whole visible range, and over 80% of the incident photons, the photons that hit the cell, are converted to electric current. Sometimes we even get 90%, and so the dye is as good as a top-notch quality silicon cell in terms of visible light harvesting. But of course, we use much less dye, and the production is much cheaper of those dye molecules. And so here's some, before I pass to the perovskites, here's some of the commercially produced panels. And so recently we have actually had a quantum jump in the efficiency. And this was due to the introduction of the redox copper 1,2 redox shuttle. And again, we should give Marina Freitag and Anders Schagfeld credit for having driven this development of the copper redox shuttle. And so, yeah, so we're looking forward, of course, to working now on going further up in the efficiency. And the Nature paper that reported on these results was published in just 2 years ago. And here, this 3 Chinese postdocs that really did an excellent work for this this important publication. And yeah, I just want to come now to that's the last point I mentioned before we go to the perovskites. When we talk about ambient light, like now when I look outside, we have a cloudy sky, then the energetics of energy conversion are different, because there's no or very little infrared radiation in the diffuse light. And so the short peak Grätzel limit, which is the optimum band gap of your absorber, shifts to the blue. And this is particularly true for LEDs, for light energy, for light emitting diodes that are used as indoor lightings. And so instead of having 32%, that's a solar to electric conversion efficiency. With this kind of light, the diffuse light, we get much higher efficiencies. And for example, over 50%. And so that's a real worthwhile source to recapture indoor or diffuse light and convert it back to electricity. And the DSCs are on top. They have reached the highest efficiency amongst the emerging and also conventional photovoltaics. You see alpha silicon, that's amorphous silicon, is much lower. And crystalline silicon would be even lower because it doesn't have the right band gap. You see, optimum band gap is 1.8 EV. With a sensitizer, you can easily get to this absorption threshold, but silicon has a too low a band gap, and so the efficiency falls very steeply when you go to the right. And so, yeah, I mentioned the ambient light harvesting. And École is a company in Sweden that was founded in 2014. And you see the Swedish king is here in the middle. He liked the photovoltaic molecular technology. And this is Giovanni Fini, the CEO, and Henrik Lundström is the technical director of the company. But they're really, I mean, the two are extremely good duo, and they have pushed the company now to major accomplishments, like putting products on the market. And this January, there was a the biggest worldwide consumer electronic show is in Las Vegas every January, and they had the largest pavilion, and that's in the main hall, and they showed over 11 products that are produced now from dye-sensitized solar cells. Now you might wonder why these cells look black. This is because carbon is used as back contact, so the dye color you can't really see. Here are some other applications like this remote control, and you don't have a battery problem anymore. They are or self-powered or portable speaker. They don't need battery anymore. So it's really a battery replacement in many ways. And so that is something that really kind of revolutionized not only this field, but the IoT. IoT needs billions of nodes that could all be powered by the dye-sensitized solar cells. And Bamipin Photonics, a company that was created 2 years ago in California, they actually target the IoT market for their cells that are also very nice, very efficient dye-sensitized solar cells. And so, as I mentioned initially, the perovskite cells emerge from DSCs. And so what is so special about the perovskite? Well, they have a lot of attractive properties, like strong light absorption visible. It's listed here on the slide. And yeah, but one of the real unique features is the orbitals. Both the HOMO, which is the valence band maximum, and the LUMO, conduction band maximum, they are anti-bonding. So that's the amazing feature about these cells. And so when you break, say, a lead iodide bond, this is, the formula is MAPBI3. So if you break that bond, it actually stabilizes the system. While in silicon, if you break a silicon-silicon bond, you would make a very deleterious defect in the middle of the band gap. And so this technology started with Miyasaka's work on DSC that use nanoparticles of methyl ammonium iodide, the perovskite, as sensitizer. However, these they were unstable in the liquid electrolyte because I mean these are ionic crystals that dissolve in polar solvents, and so so the switch to the solid-state hole conductor was key to the present development, and so the two papers appeared on the. There was an intermediate step that Professor Kanatzidis from Northwestern, he published a paper in Nature, all in the same year. There were 3 papers published in 2012. And here he was kind of a hybrid, a dye-sensitized N stands again for Nasruddin. And so we had dye-sensitized CO2, but he used a whole conductor that was a perovskite, a solid-state device. And so he found that perovskite did some co-sensitization. Then, I mean, these are perovskite cells per se, they have no other absorber. And 2 papers appeared, and we're collaborating with Namgyu Park on this pioneer study. And these 2 papers all use the Spiro now. The spiromeotide, that's a triarylamine whole conductor. And that was already published. This work was, this molecule was used for DSCs, for solid-state DSCs, much earlier, like 14 years earlier. You can see you do fundamental research, and then all of a sudden, in a decade later, you can use that to your advantage and make a major advance or breakthrough. And so the cross-sectional picture of a perovskite solar cell is shown here. It's like the dye-sensitized has a conducting glass and then mesoscopic TiO2 or tin oxide, and but the main absorbing is actually the layer on top of, which is the perovskite solar cell, perovskite photovoltaic material, and then you have you have electron selective contact and hole selective contact, and that's all you need for photovoltaic cells. You don't need a p-n junction really. If you have 2 selective contacts and you have a photoactive material that produces the diffusion lengths, the carriers, that must be at least as long as the light absorption length, which in the perovskite is about a half a micron. And so the diffusion length of the carriers is several micrometers. So you can capture the carriers before they recombine. You don't need an electric field to separate it. It's very similar to dye-sensitized cells, where the carrier lifetimes are in the second domain, hundreds of milliseconds. So even though the diffusion is not very fast in the DSC, we can capture those carriers. And the perovskites, the diffusion is fast, and so recombination also faster than for dye-sensitized. But you have that product of fusion coefficient and lifetime is large enough to ensure that you capture these charges. And so a couple of years ago, we had the first prizes given in the UK, in London, for the rank prize for these inventors. And yeah, I like to also mention an early book that kind of gives a nice review of what the earlier contributions to the field were. And you see the three authors, Namgyu Park and Miyazaki and myself. So but of course, we didn't write that book. There were many contributions. And so today we have a very nice progress, and the efficiency is now at 26.7%. That's certified, and the tandem with silicons have 34.6%. So they beat the Shockley quasar limit, the silicon perovskite tandem. Yeah, so we have done a lot of studies that would take me hours to summarize all of this. So what I prefer to do is to just show you an example of how progress was being made and how we get to high stability. And it's just very, very important now to have scale up happening and show that these cells can last in outdoor operation. And the challenge is to meet silicon stability. Now, silicon has an incredibly good stability. Over 1 year, the efficiency declines only by 0.5 percentage point. So, in 25 years, you lose about 12%. And that is really a challenging target. Now, can we reach that currently with a perovskite solar cell? No, but you're making very good progress. And I'm showing you now an example of how progress was being made. So first of all, I mentioned this particular A-cation, which is called formamidinium. The formamidinium letter iodide is actually preferred composition formulation for photovoltaics. It has the lowest band gap. So optoelectronic properties are superior to other A-cations like cesium or methammonium. However, there's a big drawback, big caveat. This phase is not stable below 100, say 60 degrees Celsius. And so, yeah, I mean, it doesn't serve any purpose if you have a photovoltaic material that converts to an ineffective, actually a phase that is not only photovoltaically ineffective, but it also produces recombination reactions. And so you don't want this in a mixture. So how do you maintain this alpha phase? And so, yeah, it was discovered that when you mix A-cations like cesium and formamidinium, then you can stabilize the black phase. And see that very clearly here. They start with the yellow phase of both compounds at room temperature have the yellow phase as more stable. But when you mix them in a mortar, you can do a mechanochemical synthesis. We pioneered that with Professor Lewinsky from Warsaw. And so if you mix those in a mortar, it turns black. And so that's a magic way. So today's formulations are the preferred formulations are these combinations. The cesium, say 5%, and the rest is formamidinium. And so these are certainly the formulations that people use now in commercial perovskite cells. And so, however, there was a drawback with the cesium when you use those mixtures. And I should mention to you, the films are made from solution processing. So you have the precursors in solution, and then you spin coat the material, the ink on the conductive support. And then you add an anti-solvent or you move the solvent, and then precipitation of the perovskites happen. However, what happens with these formulations is the cesium precipitates much faster than the formamidinium. So you get some inhomogeneous distribution of the cesium across the film. And so that needs to be controlled. And in a recent paper that came out in Nature, we joined paper with the Nankai group. We we found that this inhomogeneity can be controlled by adding acetate as a agent that would slow down the crystallization of the perovskite, so that you don't have that accelerated precipitation of cesium-rich phase, and which creates all sorts of problems. I don't want to go into details, but one is efficiency, and the other one is stability. And so by using this this acetate as an additive, we go through intermediate phase, and the crystallization is retarded. Oops, I'm sorry. And so, yeah, in a nutshell, that gives you cells that are over 26% efficient. And then you can see the stability. That's really now becoming the most important parameter. Can you show long-term stability? But of course, we cannot wait 25 years to see how well the perovskite solar cells do outdoors. And so, although outdoor tests are ongoing, they are slow. So how do you get an answer whether your formulation in your cell is stable or not? You have to do accelerated tests. And one of the most challenging tests is to have the combined stress, high temperature, high humidity, and maximum power point tracking. Maximum power point tracking means that you keep the cell at the maximum power point of the voltage. So there's always a voltage, and it's a voltage that gives you the maximum power output, the maximum efficiency, if you like. And you can see that just by using that simple trick with the acetate, he gets now a result where over 2,000 hours of full light soaking, and you have humid, and you have the maximum power point. So it's high temperature, full light, and maximum power, but the electric field is there. And still you can see, I mean, there's hardly any degradation. Now, if we now take that result and say, can I extrapolate? Yes, you can. You can extrapolate, and a result like that is comforting. It tells you that this cell would have an extrapolated lifetime of over 20 years. And so because the temperature is lower under real conditions, there's night and day phases. It's not always full light. However, there's also temperature change. And so the temperature cycling has to be done as well with those cells. And that's being done. And so we are now working on a production plant in Turkey with a group called Güneş perovskite solar cells. And yeah, the goal is to make cells that are based on carbon as a charge carrier collector, as a back electrode. And yeah, and so this is now on its way. And yeah, we should have the pilot ready actually this year in Adana, Turkey. And so, yeah, I start with the dissemination, and now I finish rather with education. And so, yeah, I mean, many years ago, just in the magic year 2012, I was invited by Bill Gates to see him. He was interested in our research in solar fuels also in particular. And so, we went with, I went to see him in Seattle. He paid for a business flight to Seattle from here just to talk to us. Nate Lewis was the other scientist who was in a discussion. He's a professor at Caltech, and so for 4 hours discussion with Bill, and then yeah, he became intrigued by the idea of making solar fuels. Here he's visiting Nate Lewis' lab at Caltech, and he set up a breakthrough energy fund that it's called Breakthrough Energy Vendors. And I know several startup companies that have been funded. So I draw your attention to if you go on the internet, you can find their website. And if you want to raise money for for solar-related fuel production or electricity production, you can apply to this fund. They have now collected over $1 billion. And at the end, I mean, we have to motivate the young generation, and so the dye-sensitized cell is unique. I mean, you can have young kids make themselves a solar cell. You couldn't do this with silicon or even perovskite. So the dye-sensitized, it's simple. And the only thing you need is you have to have a source of dye, and so you can use berries. And these berries have for example, blackberries or raspberries, blueberries. They have this anthocyanin dye, and you see the two hydroxyl groups. They attach very firmly to the TiO2, so they form a self-assembled monolayer. So if you dip the TiO2 film, which you see here, these cells, just in these pulp, the fruits, you smash the fruits and you make it. If you dip them, the dye there will be an uptake, and you can wash the cell. It will be highly colored. Okay, because of the mesoscopic structure, which has very high internal surface area. And here you see the voltage is 604 millivolts. That's not bad at all from an indoor or outdoor measurement. And even have gone to the younger generation, and you see how the young girl is infatuated by making this solar cell. So we have to also reach out to the public and to younger generation to make them sensitive to the climate issues and how we can solve them or contribute at least by harvesting light via photovoltaic effects. And so just mention that there was a competition a year later in Sweden. What's the best dye? Natural dye. And so a lot of schools participated. But I'm not sure what came out of the winner. I have to ask my colleagues. So with that, I spoke my 45 minutes, and I want to give credit to our funding organizations, and this is our group. And you see behind, this is the dye-sensitized solar cell facade on the Swiss the Swiss Tech Center in Lausanne. Okay, with that, I like to finish my talk, and I thank you for your attention.
So you can either write in the chat or raise your hand and unmute yourself and ask the question directly.
Can I ask a question?
Yeah, please. Go ahead.
Thank you so much. Thank you for inviting me to the prestigious lecture today, and the continuous acknowledgement to our Professor Grätzel for the fantastic seminar today. Sure. I would like to ask the professor about the fourth generation of the solar cells. I am interested in employing nanotechnology in solar energy. Recently, I have published a book entitled Quantum Dots, Synthesis, Characterization, and Optical Investigation by IOP, a publisher in UK. So, do you think that the quantum dots could be the fourth generation of solar cells? Thank you.
Oh yeah, actually, quantum dot cells are very close to the dye-sensitized cells. The initial perovskite cells were actually these are nanoparticles or quantum dots of perovskites that were used to sensitize like the mesoscopic structure I showed, that there is a quantum dot analog, and yeah, today's quantum dot cells, they have reached. I think they're made out of perovskites. The ones that are most efficient are using perovskites, quantum dots. Now, the efficiencies are, I think, very similar to our DSCs, and maybe even a little bit higher. I have to go back to the annual chart and check that. And so, yes, absolutely, this is a viable concept, and yeah, there's room for new, perhaps new structures, new combinations, new quantum dot materials, and so yeah, I would definitely encourage you. We ourselves have published also on quantum dot cells with that Sargent's group. He used to be in Toronto, but he's now at Northwestern University. Like in 2006, we published a paper on using lead sulfide quantum dots in a solid state mesoscopic solar cell. However, that efficiency was not very high. I think was only 5 or 6%, but it showed the feasibility. You know, the efficiency is one thing, but science is more important. You have to try to understand how, deeply understand your system. Then you can make progress on the efficiency front.
So thank you very much. If we have another questions, we can have a time for one more. Okay, if not, then can I, Grätzel, have a question? What do you see as the pathway for the future that this any new technology the society can use? Do you think that in the next 5 years it's going to happen and we can see a wide scale deployment of any type of emerging solar cell technology?
Yeah, I think that the third generation, we call them third generation, is developing now at a very rapid pace, and progress is being made on the efficiency and stability front, and the scale up also is happening. And so now there are panels that are over 2 square meter size, okay, and so you showed one of those. They were not quite as big, but I just heard today from China they have now even bigger ones. Now the issue is that commercial sales have to start, and as so far, I don't think perovskites have started commercial sales. However, the Dyson starts certainly since many years already, and so yeah, the applications will be in very different areas, and silicon will remain a very powerful and useful partner on this long journey, which, you know, in the next 20 years, we have to reach the 75 terawatts. And if not, then we have really big problems. I mean, the emergency, the climate change, and all of this. That we should keep in mind. We should keep it in mind.
Right, we have a huge requirement. The requirement is very high, and the pressure is very high, also high on society. So we hope that either of this technology will come up, and the Asian countries are pushing very high. The panel I showed, Nazir has passed me this information, I think, a couple of months back from a Chinese company of 2 meters by 1.5 meters square.
Yeah.
These companies are pushing a lot. So if there is no further question, I think I like to thank Professor Grätzel once again for his master class on photochemistry, and also to young researchers, also to our academy member for joining us. And with this, I think, Sara, do you have something to say or no? Okay.
Can
So,
I now? Can I one question? More question?
but be concise, please.
Yeah, sure. Prof, for the efficiency of quantum dots is around 5 to 6%. So if we have implemented for one panel of different sizes of quantum dots, do you think the overall efficiency could be increased? Thank you.
Well, so far the quantum dots are not quite as efficient as the perovskites. They are made out of perovskites. I don't see any quantum dot cell that gets over 10%, which is not made out of perovskite. And so now you have to compare. Is it better to have quantum dot and perovskite, and at this stage, I would say, well, the solution process films, they're more efficient. However, we have to be very careful and not be dogmatic and say, oh, well, that's what, when I was young, that's what people were saying about Dyson-sensitized solar cell. It's a lost case, don't work on it, you're wasting your time. And so these kind of statements are absolutely wrong. These are interesting, quantum dots are interesting systems, very interesting systems. And we have a colleague, Kovalenkov, Professor Kovalenkov in Zurich, who is a world leader in quantum dot technology, and they're being used also for quantum computing and single photon emitters. So this whole field is very, very interesting, and so photovoltaic applications are there. It's just I mean, now we have this momentum is on the solution process, okay, because you can make large areas very, very easily, and they're more efficient. But that doesn't mean that in the future this will always be the case.
So thank you very much. We are perfectly on time. So we have a 1 hour pass. And thank you again for all of us, our Academy member, for joining us today. Thank you again, Michael.
Thank you.
Thank you for your time.
Bye-bye.